Okay, look at the performance comparisons. What I've done here is compared Emdrive spaceplane plus its orbital module with a standard Atlas V, which is the current large launch vehicle. I've compared it also with a projected UK Skylon spaceplane with its upper service module, SUS. Not quite sure what that stands for now, but anyway, it's an upper module. It gets you again from LEO to GEO. So if you take a quick look at the figures here on the table, launch mass for Emdrive is roughly the same as Skylon, around 300 tons. Compare that with a total lift-off mass of an Atlas V of about 540 tons. Emdrive gets you almost 50 tons into GEO, whereas Atlas and Skylon, you're talking about the order of 3 to 4 tons. What is extremely interesting and gives people cause for thought is if you actually use Emdrive to launch into LEO as opposed to GEO, you can't achieve such a high payload mass. In fact, it's brought right down to something like 16 tons and now becomes comparable with the Skylon and Atlas. And the simple reason for this is that the whole flight concept for Emdrive is completely different to the classic launch dynamics of either a rocket or a space plane. Essentially what you're doing is obtaining the altitude in a very low energy vehicle, and a large amount of the energy is required to gain orbital velocity. Well, low Earth orbit has a much higher orbital velocity than geostationary orbit, so you are not going to be able to launch such a large payload mass. To a lot of people this is counterintuitive, and you literally have to go through the sums before it all becomes clear. Major factor in the cost driver is the fact that the Emdrive spaceplane is a very simple construction. The airframe can be no more complicated than a current aircraft airframe. It, as I say, has very little mechanical and thermal stresses on it. And this helps to bring down the cost per launch by increasing the number of launches, and we've put a typical launch number of 500. The reality is, of course, that this will probably be much bigger than this. Again, the idea is to achieve not only airline operating procedures on the ground, but typical commercial aircraft lifetimes. So, but nevertheless, we put it at 500 as a conservative figure. The end product of all this is that it reduces the cost per launch from something like $110 million for Atlas V, which is the current asking price for a launch, down to something like $11.2 million for a typical Emdrive launch. Now, not only that, of course, is you're launching considerably more payload mass, so that if you look at the cost per payload to geostationary orbit, or geosynchronous orbit as it's sometimes called, you're reducing the almost $30,000 per kilogram of a typical Atlas launch to our calculation of $224 per kilogram. And that, of course, is a huge cost saving and completely changes the whole dynamics of the launch industry. So if we look at the sort of things that we can do with this launcher, the big application that comes to mind is space solar power satielites. There's been a lot of work on solar power satellites. It goes back something like 40 years. And the current state of the various studies is probably well summarised in a 2011 report from the IAA, which essentially said that there are no fundamental technical barriers that would prevent the realisation of large-scale SPS platforms during the coming decades. The most critical challenge, however, is the essential requirement for very low-cost Earth-to-orbit transport. Just to give you a sort of example of what this means, to get 2 gigawatts of power from a solar power satellite, which is, if you like, similar to the output of a nuclear power station, you need to get 6,700 tons into geostationary orbit. If you use Emdrive space planes, we could do this probably over about a year by using 3 space planes, launching about once a week, and using robotic assembly, all of which is sort of quite a reasonable approach to building something 6,700 tons in orbit. The total transportation costs, we believe, will be of the order of $1.5 billion to get this 6,700 tons into orbit. Now, so this is it's less than a tenth of what the IAA study requirement said would be necessary to make SPS viable. They were suggesting they need to spend, they need to bring the cost down to about $20 billion. But compared to the existing costs, it's a remarkable drop. If you are currently flying 6,700 tons to geostationary orbit, you would need 1,700 Atlas rockets, and the total transportation cost would be the order of $194 billion. So the reality is that solar power satellites are not going to happen until we can reduce the costs very, very dramatically. And what I'm suggesting is that Emdrive is the only viable proposed technology that can bring the cost down to make it SPS viable. Now, if you're actually proposing putting large masses into orbit to generate power for the Earth, you might also consider what else you could use these for. And the classic, or a classic approach to the raising global temperatures has been why can't we put a sunshade in space? And indeed you can, and again the physics is well understood and has been studied for many years, but again it's the large cost of putting huge masses into orbit that tends to reduce the probability of these ever being taken seriously. But just looking at the total energy requirement or power requirement of the Earth, in 2008 it was something of the order of 16 terawatts. Now, recent studies have shown that if you wanted to reduce the temperature of the Earth back down to its temperatures before global warming started, you'd need to reduce global solar radiation by a factor of about 1.7%, and this would require the launching of something like 2 by 10 to the 7th tons of reflectors or sunshades into orbit. Now, when you compare that with the masses of solar power satellites, you realise that you would actually get to that mass once you'd launched 3,000 solar power satellites. And that would still only give you about 40% of the power requirement that you're going to need on Earth. So the reality of all this is that if you use solar power satellites to provide all the power that the Earth requires, the actual mass that you would put into orbit will be of the order of 3 times what is necessary to cool the planet. So clearly there is synergy available in these two engineering proposals. and we would need to think in terms of deploying solar power satellites perhaps to the Sun-Earth L1 point rather than geostationary. We would probably use laser power transmission back to geo to get the power to geostationary orbit, and then microwave from geo to Earth. But it would put the solar power satellites with their associated very large reflectors in just the right place to provide shading for the Earth. So what you have then is the possibility of solving both the Earth's energy requirements and the need to reduce the Earth's temperatures, all in one solution, and one that is not the sort of science fiction that it would be if you were trying to do it using existing launch technologies. Okay, what else can we use second generation Emdrive for? Whilst we were studying the launcher, we also looked at, hey, could we use this as a long-haul transport vehicle? The end result is a very similar looking vehicle. Will take you from London to Sydney in 2 hours 40 minutes. It'll get you city centre to city centre because it's vertical takeoff and landing, and it's also very quiet. It actually doesn't make any noise. It uses green energy. It's liquid hydrogen fuel. It would get typically 100 first-class passengers backwards and forwards in great comfort, with a cost per passenger mile that is actually below the existing costs of a typical airline. The flight profile is interesting and illustrates the completely different approach to flying that Emdrive will give you. You have vertical takeoff, a very slow ascent, going up using an auxiliary jet as propulsion, and Emdrive for lift. It takes the order of 20 minutes to get you up to your cruising altitude of, in this case, 100 kilometres. Now here you are not completely free of atmospheric effects, but to all intents and purposes you are in the vacuum of space, so you can start to accelerate without all the thermal problems that you normally get. You actually accelerate up to a few thousand miles an hour. Such that your cruise phase lasts of the order of half an hour. Again, you restrict the acceleration to something that keeps your first-class passengers comfortable, well below 1G, so you wouldn't really notice it. At the end of the cruise phase, when you're sort of over the coast of Australia or wherever it is you're going, you start to descend. Again, you're using now Emdrive in the reverse mode to control your descent. Again, it's a gradual descent, and you finally turn on, when you're down into the atmosphere, you finally turn on your jet to give you the manoeuvrability to approach your car park landing space in the middle of the city. Now, all this is completely viable. It's different, it's disruptive, but it's completely viable, and it is cheap, because suddenly you have a long-haul aircraft that is not difficult to build. We were looking at the details of this, and one of my colleagues jokingly suggested that you could build this aircraft out of pressed steel. And it would still fly quite happily, and that's true. So in some ways you could be in the situation where you are de-skilling the building of an aircraft. You're moving from the existing high-tech, highly skilled method of building aircraft to basically automobile manufacture. So clearly there is disruption for the aircraft industry here. Other markets, well, a new scientist once gave a cover illustration of a personal air vehicle, which I always felt was rather nice. But it does illustrate that clearly the famous flying car suddenly becomes possible. So you can envisage automatic passenger carrying vehicles, you've got clean, quiet, vertical takeoff and landing operation, and effectively you have door-to-door transportation. Above all, you eliminate traffic jams. As soon as you start going into transport systems that are in 3 dimensions instead of 2 dimensions, you clearly have the potential for uninterrupted journeys. The actual control of these journeys is pretty straightforward. The amount of data you need to flow around a control system for automated flight of this sort is relatively low compared to modern data communication systems, it's completely feasible that we could have a totally new personal transportation system that solves virtually all the problems of our existing traffic. Space applications clearly keep coming to mind. There's space tourism, there's exploring the solar system, there's asteroid mining, and one of the latest studies we've done is actually for the first interstellar probe, where we believe we can actually reach 2/3 of the speed of light in about 10 years using a nuclear power source and an Emdrive propulsion system. Other transport applications, marine is one that has been suggested. Oil tankers and container ships can be propelled about 1/3 of the existing fuel consumption. You can also use Emdrive for stabilisation and in-harbour manoeuvring. A very interesting transport application was proposed whereby apparently one of the major problems of running railways in cold climates is the traction problems that you get. So suddenly when you don't need to grip the rail, if you use Emdrive as a lift engine, you eliminate all those problems. And of course, if you have to haul large structures or heavy goods across difficult terrain, clearly an Emdrive type hovercraft vehicle would be ideal. So, summary. Emdrive is going to give you a quantum shift in energy and transport. It's going to be an enabling technology for solar power satellites, which have been acknowledged by people who have looked at it very carefully as the only real solution to the Earth's energy problems long term. It gets rid of carbon-based fuel for future transport, replaces it with hydrogen. It's a very disruptive technology. A lot of vested interests are going to suffer, but it will lead to a truly sustainable modern world. And if you want that sustainable world to remain at a reasonable temperature, it would also enable the sort of ambitious geoengineering solutions to be implemented. This next slide, but what it does, it presents a possible roadmap to the development of Emdrive. It starts off back in 2003 with the history, takes us through to 2013, states where we are now, and gives some potential milestones en route to 2023 for the next 10 years, when we should end up with personal air vehicles of around 1 tonne, 1.2 tonne mass. We'll have spaceplane launchers 320 tonnes, 50 tonnes to geo payload. We'll have VTOL transport, long-haul transport. 100 people taken around halfway around the world in less than 3 hours, and we'll have deep space propulsion modules. Now, all this is quite feasible, and the roadmap to get there is has been planned. So, how are we off in terms of actually starting along this roadmap? Let's look at the different countries in the world. First of all, take Europe. It's fair to say that until very recently there's been no major interest in Emdrive within Europe. Industry, particularly in Europe, tends to be very conservative and is heavily committed to small improvements of what is still essentially 20th century technology. Ourselves, we're continuing theoretical research at SPR. We've recently completed a design study for an all-electric single-stage to orbit launcher. This is to basically, as an improvement to the hybrid spaceplane we were talking about earlier. In America, things are interesting. There are clearly many defence applications which are taken seriously, but to date there's nothing in the public domain. There is a superconducting research program going underway in one private company, though the results to date aren't exactly very impressive. But they're making progress. China is actually the country that seems to be leading the world. The basic research, as I understand it, is now completed. Papers have been published. Even the UK Institute of Physics has published one of their papers. So that certainly makes it respectable. They have a superconducting research program underway, and I believe there is significant commercial space interest within China as well as just the academics. So we have a situation that Europe needs to wake up. Otherwise we will literally be left as a museum of 20th century technology. And more importantly, we will be unable to contribute to solving the major global problems. And we'll be just shrugging our shoulders and leaving it to either America or China, or probably both.